We've been learning about scope and storage all semester without formally defining them. And now in Chapter 10 of King in our study of C, we're going to more formally define them and go over some of the things we already know, hopefully learn a couple of things we may not know. So scope, right? Scope means the accessibility and visibility of variables at different points in the program. Remember, we learned that if we don't declare a variable, we can't use it, and we can't use it until after we declare it, is what we've learned, right? So variables or constants have four types of scope: block scope, which is what we have seen when we declare something inside of main; function scope, well, now that we're writing functions, we'll see that variables have scope or visibility and availability just local to that function. Right. File scope, we only have one C file at this point. That really won't affect us. And program scope also relates to multiple files. Right. So for block scope, we're referring to a group of statements that's enclosed within opening and closing curly brackets, right? We've been doing that with main, we've been doing that with the functions that we write. So anytime that we declare something within that block, as soon as that block exits, so as soon as we get to the ending curly brace, the variable ceases to exist. We also refer to this as a local variable when we say that it has block scope. Right. So we're going to take a look now at this example program called while block scope. So I'm just actually going to escape out of here. Let's pop up code blocks with the same program in here. All right. So I've got some comments here. I'm declaring X right here within main, right? We've done that before. We declare the variable and I'm also initializing it, right? Anything that we declare locally inside a block has a garbage value, right? So here I'm initializing X to 10. So its scope, so the scope of X is local to the function main. It will go out of existence when the main function stops. Well, we know that the main function stops whenever our program stops. Right, as soon as we get to this return statement. Right. Here we're going to print out the value of X, so we're outside the while loop. So I've got a while loop down here, so here's another variable I. I've initialized it to 0. We're going to say that while I is less than 3, we're just going to come in here and declare another variable named X. When we do this, this X will actually hide access to the X outside here. This X will no longer be visible. This will be the only X that's visible to the while loop because it's defined within this set of curly brackets. So it's nested within this block scope. Right, so we'll see that as we iterate through this, we'll just print out the value of X, which is I. We'll increment I by 1. So we should see that I equals 0, I equals 1, I equals 2, because when I equals 3, this test will be false. We'll drop down here then, and we'll see then that when we refer to X, we'll be referring to the X that was declared up here, outside of this block. Right. Let's just go ahead and do a run to cursor. Right. I've already built this. All right, so run to cursor, right? Nothing on the output screen because I haven't executed that code yet. You can see here that we've got X as a local variable with a value of 10. I just has garbage in it. So next line. Right. So next line, this executed then this printf statement, we see that we get the message that the value of X outside the while loop is 10. So next line, we'll set I equal to 0. We'll perform this test. It will be true. 0 is less than 3. So we come in here, and now then this local X that's local to this function should be equal to I. All right. So the debugger is not showing me that X without me adding it, right? It's still showing me the X that's out here in main. This X I just added is local to this block, right? It has a value of 0 because I has 0 and we assign that to X. And so when we print that out, right, we see that value of X inside the while loop is 0, right? We'll execute the next statement, add 1 to I will become 1, 1's less than 3. We're going to set X equal to I. So once again, this X prints out, right, value of X inside while loop is 1. We executed these statements, so now I is 2, but 2 will be less than 3. This test will be true. We're going to assign the value of 2 to this local X, right, local to this block, right? And then we'll see that we printed out value of X inside while loop is 2. I is now 3, so this test will fail, right? So our next line of code executed down here. The only X this knows about now is the one that was declared inside this block here, right? This value that X has a value of 10. Right, when we execute that statement, we get the value of X outside the while loop is 10. Right? And when our program ends, we wouldn't have access to any of these variables. Right? Now, it's not the best idea to actually then give the variables the same name within the same scope, because when you do that, let me clean out my workspace here. When I compile, I'm going to get these warning messages, right? Letting me know, warning, declaration of X shadows a previous local, right? Because I have the -W shadow warning turned on. So that warns me then when I'm going to hide some other variable that's declared. And so it's not the best practice to hide variables by giving them the same name, right? I'd have been better off naming this Y or something like that. So since this block is within another block, right, I'd be better off giving it another name. But you can give it the same name, you just need to be aware of what happens. Right? And so there's that example then of that while loop. The next example we're going to take a look at is in a program you've been given called FunAScope. Right? It's got a function, so we want to see that the variable's active and visible from the beginning to the end of a function. So let's just pop up that example in code blocks and step through that. So I'm going to add this file to my project. I'm going to remove the other file. So this is our file, funascope.c. Okay, in here, let's look at main. We've got, then within main, we're declaring a variable named X. So X is declared within main, its scope is local to main. It's going to go out of existence when the main function stops. Right, so we'll just go ahead and print the value of X here in main, and then we're going to call function A. When we call function A, we're going to pass the values of -13 and Z to these parameters. So we'll see that A gets the value of -13, B gets the value of Z. And as we step into this function, you can see here we're declaring a variable named X. So this X will only be visible, right, and accessible from within this function, right? So we'll go ahead and print out the values of X, A, and B in the function, and when we leave this function, this X goes away. We no longer have access to it. So when we leave the function, we go back to where the function was called, which will be from within main. We'll come down here and we'll print out the value of X inside main, which happens to be this X. All right, let's just go ahead, rebuild, do a run to cursor. All right. All right, so here in main, my only variable X has garbage in it because we haven't executed this initialization yet. So next line, now we can see X has 10. Right? If we execute the printf statement, we can see then that printed out that the value of A outside outside of function A is 10. Right, now let's step into here. All right, so step into, now here, notice we've got two function arguments, A and B. A got the value of -13. The first thing in the list is then a copy of that is assigned to A. Right? The second thing in the list, a copy of that is assigned to B. So A and B will only exist as long as we're inside this function. As soon as the function leaves, we don't have access to A, we don't have access to B, we don't have access to X. Right? Now, when FunA accesses X, it's the X that's defined within here. It has no access to this X down here. All right. So next line, right, we assign 5 to X. We're just going to step through, right? We print out this information. Right. We can see that inside here, X was 5. All right. So now if I hit next line, we can see we're at the end of this block, right? We return back to main when we're ready to execute the line right after our function call. So back here in main, we can see we're referring to this X again. It has a value of 10, right? It's local to that particular block. Right, we print that out, and our program will end as soon as we execute the return 0 statement. Right. So this X is local to this function, this X is local to this function. Right. Now that we're back in main, we can't access any variables named A or B because we haven't declared anything called A and B. Right. Those were only local to this function up here. All right. So you're probably starting to get used to this now. that we're writing functions. All right. Okay, program scope then. We start talking about global variables. Right? Global variables are declared outside of function blocks. We've declared a couple of examples of global constants before. Right? Constants are variables that are read-only. Once we declare them, right, they can be accessed from any point within our program. So global variables, the lifetime of a global variable, right, it's created at the beginning of program execution and it remains in existence throughout the period of execution of the program. So anytime when the program's running, we can access a global variable. Its lifetime exists for the length of the program. We can access it as long as we're not hiding it by any other variable of the same name. Right. So when we declare it, it's recommended. Sorry about that. It's recommended to declare them at the top of the program code. Right. We declare them outside of any functions. So if a variable is declared that has the same name as a global variable, it will hide it. Right. So we'll see an example of that. The function we use the local variable and ignore the global. The recommendation is that local variables don't have the same name as global variables, so you avoid this whole naming conflict. So what we'll do now is we're going to take a look at this global x.c program. So we'll add this one to our project, and we'll remove fun A from the project. All right, so now we have this file here where we're declaring a global variable, and I've misspelled initialization. All right, so here, x is a global variable because it's declared outside of a function, right? It's declared outside of any curly braces. So we're declaring at the top as recommended. It still has to have a data type. It still has to have a name. We don't have to initialize it at this point. I'm just doing so that we have a known value. All right, now, our program will start execution here in main. Let's just go ahead and do a run to cursor. All right, so now that I'm in main, notice it only shows me my local variables. It doesn't show me my global value of x. So if I say x here, if I add it to my watch list, it gives us this x, which is global, right? We initialize it to a value of 77. And now if we go ahead and execute this printf, we'll see that we actually get a value of 77 for x, right? X is 77. Because here, we're referring to the global x. Main hasn't declared any variable named x, so the only x it would know about would be anything that would be global, which in this case there is one, right? So it referred to that area of memory. Right, now, if we call this function named fun_a, we're going to pass it the value of 13. Notice once we get inside of fun_a, though, it has a parameter named x. So since this parameter has the same name as the global, anytime we refer to x within this function, we'll be referring to the local x, right, which will have the value of -13. All right, so if we say step into, right, so now we're up here in main, right, function argument -13. You can see then the x in my watch window down here that used to be our global has to be the local. It's hiding the other. Right? Whenever it has the same name, it hides the global. So anytime we refer to this x now, we refer to it as -13, or it has the value of -13. Right? As soon as this function ends, this x will go out of existence. So we'll just execute this statement. Right? So we can see that it prints out in fun_a parameter x is -13. Now when we leave this function, this parameter goes out of existence. So now that we're back down here in main and we're referring to x, we're referring to the global x, right? And if we execute, once again, if we execute this statement, we can see then that we print out global variable x after fun_a is 77, right? Because this one went out of existence. Right, so you see an example of a global variable, you've seen an example of how using the same name hides it, and so what global scope means, right? Oh, okay. All right, so file scope. So global variable is accessible until the end of a file. Well, we only have one file so far in our example, so we say that it has file scope. Now, when you have a C program that has multiple files, if you only want to allow one file to be able to access that, we use this keyword static. And that's when we really talk about file scope as opposed to program scope. Because before, right, we were talking about program scope. We were talking about a global variable being available anywhere in a program. We simply have one C file, so that's available in our file. But when we have multiple files, we can use the keyword static. So a global static variable can be used anywhere from the file in which it was declared, but it's not accessible by other files, right? So later when we write programs that have multiple files, we'll come back to an example of this, right? So storage, we talked about scope. Scope is when something is available to us, so accessible and visible, right, to our code. Storage talks about then where it's stored in memory. So storage classes, right? The storage class of a variable defines the scope and visibility and the lifetime of the variables or functions declared. So functions have visibility and they have a lifetime as well too. Right? So the storage class determines what part of memory where the storage is allocated. So most of our memory is stored in main memory. So some people call that RAM. There's different levels of RAM or cache levels. There's different levels of main memory. So if you want to think of that as RAM or main memory, that's where most things are stored. We'll see that it's possible to have a storage class that stores something on the CPU registers. Right? The storage classes then will specify how long the storage allocation continues to exist, the scope, so whether the variable and function can be referenced, and it specifies whether the variable or function has internal, external, or no linkage. Well, linkage then gets us into an area of having more than one C file. Right? So we don't have to worry about that yet. That's more advanced than where we're at. Right? It also specifies whether the variable will be automatically initialized to 0 or to any indeterminate state. So indeterminate state, that's the garbage that we know about so far, garbage values. So our 4 storage classes are automatic, register, external, and static. Automatic is the one that we're used to using. It's automatically been done for us, right? We're going to see that we can have a storage class specifier. Whenever then we declare a variable or a function, we can use this storage class specifier in front of it. Data type, so when we've declared variables, we've already declared them with data types and variable names. Well, we can add a storage class specifier as well. That's the general syntax. So the auto storage class specifier is used to explicitly declare a variable with automatic storage. Right? It's default storage. It is the default storage class for all variables declared. So everything we've been doing so far in C has what is automatic storage. It's part of the auto storage class. We just don't have to use the keyword auto in front of it simply because it's the default. So we could then, if we want to declare a variable of type int, the variable name is X, we could use this keyword auto in front of it as the storage class specifier. Remember general syntax, storage class specifier, data type, variable name. Right? But we don't do that because it's the default. Right? You will rarely ever see this written, the keyword auto. It is a keyword in the language, so we can't use it as a variable name, but anytime we've declared a variable so far named X inside of curly brackets, it has what we call automatic storage. Or when we declare it as a function parameter, it also has automatic storage. Right? It's deleted when the block in which X was declared exits. Like I said, it's used to declare variables inside a block, so inside curly braces, or the name of function parameters. The auto storage class specifier is redundant while declaring data, meaning we don't write this because that is the default type whenever we declare anything, right, in that inside the curly brackets or as function parameters. Right. So all local variables declared within a function belong to the automatic storage class by default. That's what I've been saying. Memory is automatically allocated upon entry to that block and freed automatically upon exit from that block. We haven't had to do anything to specifically free memory. Right? That's taken care of because it's in this storage class. Right? The scope of the variable is local to the block, so it's local to those curly braces. Right? Every time the block is entered, the value of the variable is declared with. So the value of the variable declared with initializers is initialized, meaning anytime we say something like x equals 3, every time we come in that block, we go ahead and reinitialize it. Right? If auto variables are not initialized when we declare them, so if we just say int x, we know that x has some sort of garbage value, and they're all stored in main memory. So on the main memory stack, right? Function parameters. So function parameters are defined inside the parentheses whenever here in the function header, right? They have automatic storage duration, right? They have local scope, but they're initialized automatically with the corresponding argument passed in the function call. So here, if I call the function myfunc, so I'm calling the function using its name, inside the parentheses, I'm going to pass the value of 3 to x, the value of 4 to y. Right, so x will be initialized with 3, y is initialized with 4. So that's what we mean by parameters are initialized automatically with a corresponding argument. This is an argument here passed in the function call. There is a register storage class, right, which is then applicable when you're working with something like interrupt service routines. It's applicable whenever we want to store something directly on a CPU register. It's faster to store variables in a CPU register instead of RAM, right? The maximum size of the variable, so the size in bytes, is equal to the register size. So if you've got a 16-bit register, you can only store a 16-bit number there, is what this is saying, right? Once you put something on a register, you can't use the address operator with that because it has no memory location associated with it, right? We use it when quick access is needed. So this comes into a little bit more when we get farther into embedded systems. We'll see that when we're writing interrupt service routines, we'll want to place information on a CPU register. Now, it may or may not be stored in a register. When we tell the compiler that we want this to have a register specifier, it's only a suggestion to the compiler. The compiler may or may not do that, right? There's a limited number of hardware resources. So there's only so many CPU registers. So the compiler may or may not comply with our request, right? It has automatic storage duration, right? And it's accessible while we're inside the block where we define it. Right. Then the externStorage class, right? So we'll come back. I haven't given you an example of this. When we need to use the register specifier, we will go through an example. But at this point, we're not working with that in class. Similarly, there's an externalStorage class as well that at this point, since we only have one C file, we will not learn to work with it. It's a more advanced topic than where we're at. I've given you an example of some files with some external variables. We will come back to those likely when we have when we start working with multiple C files. Right? You're welcome to work through those on your own if you like, but they won't be part of what we're performing here in the class right now. Right? Now, static can be used. Right? We'll see that. I'll give you an example of using a static data type within a function. Right, so static is the default storage class for all global variables, right? As soon as we place something in the global space, then it will have a lifetime over the entire program, right? It's allocated when the program begins and it's freed when the program terminates. Now, the difference about static storage classes is the default value of those variables is 0. So if we declare a global variable and don't initialize it, it will default to 0. It's initialized just once. Right, so we'll see an example of actually going ahead and creating a static variable within a function. And we'll see that when the function is called, the static variable is not reinitialized, that it retains its value between function calls. So that's a static local variable as opposed to a global variable. Right, so we use the keyword static when we declare the variable. It's going to have a permanent storage location. It's going to retain its value throughout the program execution. It only has block scope. So if you declare it within a block, it's only available within a particular block. If you declare it globally, then it is available globally. Right. We'll use a static variable whenever we, inside a function, whenever we need to retain a value between function calls. All right. So I've actually given you an example here of a program with a static variable. Let's just go ahead and bring that up and see how that works. All right, and it's actually in another location on my machine. Let me just. For some reason now my code block stopped responding. All right, it decided to come back. I was just about to give up on it. All right, let me clean out the environment. Let me see if I can rebuild. All right, let's take a look now at this function. All right, so I've got some function prototypes here. I've actually got then 3 functions declared in this program. It's really redundant to write a function prototype for main. Execution always starts with main, right? But I've then written the prototypes for my function and static X. All right, so let's take a look here. We're going to look at the difference between how my function works and the function static X works. So here in main, we've got this for loop going. We're actually going to go through this loop 10 times. We're going to print out while we're in main what the value of this X is. Then we're going to call my function. We'll drop into my function, and we'll see that we declare an X here. We're going to assign it a value of 15. We're going to increment that X by 1, and then we're going to print it out. We'll see that when we're in my function, every time we come into my function, X will be initialized to 15. We'll add 1 to it, it'll become 16. So every time we're in here, we're just going to end up printing out X equals 16, right? We'll return back to main, and then we'll call this function static X. Well, this function that I named static X has a variable declared in here with the name of X, but it's got this static specifier. So the first time we drop in here, we'll initialize X to 15. We'll add 1 to X, so X will become 16, and we'll print out 16. So the first time in each one of these functions, we're going to have the same value of X. But when we return, the specifier here says that X should retain its value. So when we come back, we'll see that X has a value of 16. The next time we add 1 to it, it will become 17. So this static variable X will continue to exist throughout the program duration. We only access it from within this block. So it's defined within this block, right? When we're back in main, main will have its own X. All right, let's run the cursor. So we start execution in main. All right, so I'm just going to delete this extra X from the watch window. Okay, I haven't initialized it, so it has that garbage value. When I say next line, now we can see X has a value of 1. 1 was less than 11. We step in here, and we're just going to print out the value of X here in main, right? So we see the output main's X is equal to 1. So now we'll step into my function. All right. So now that we're in my function, right, the local X has a garbage value. I assign 15 to it, we add 1 to it, and we print out. Oop, I accidentally stepped into printf. We don't need to see all that code inside printf. Let me step back out. All right, so now here in my function, we got the result X equals 16. Right, next line, we're going to leave this X that is local, this disappears, right? Goes out of scope. Now we'll step into static X, right? We're back in main. Main's X has a value of 1. We're going to step into static X, right? Static X was initialized to 15. We're going to add 1 to it. We'll have a value of 16. And once again, I accidentally stepped in to printf. Let me step back out. So here in static X, that X was 16, right? Do we have enough X's yet? I think we do. All right, so now we'll just say next line. So we'll return back to main. We'll go ahead and print this new line character, right? So that I want spacing in between our groups of output. All right, now back here in main, notice main's X is equal to 1. We'll increment it then. So this statement will execute plus plus X. Then it will perform the test. Will X be less than 11? It will be. Right, so once again, we'll print out now that main's X is 2. Right, now we'll step back into function X. Notice we reinitialize in my function, we reinitialize this X to 15. We add 1, we're going to get the output. I'm going to stop stepping into printf. Right, so now we get the output, my function x is 16. Right, next line, we step out of there. We're going to now step into static x. So now that we're back in this function static x, notice its x retained its value of 16, same value it had when we left. Right, we're going to add 1 to it. We'll print that out. Right, we get done. We can see then that static x that retained its value of 17. Right, now we're back here in main. Right, we'll go ahead and print out that blank line. Here in main, this x has a value of 2. We'll add 1 to it. All right, 3 will be less than 11. So if we just step through all of these, so I didn't step into them, we'll see that we get this output. Main's output will keep increasing. Every time we're in my function, that x will only ever have a value of 16. The point is this does not retain its value between function calls. Right? But this one with the keyword static does retain its value. So we'll be able to see it incrementing, right, as we continue to run through here. And if I just said run the cursor, so it stepped all the way through this loop, as we go back through, we can see then, right, that main's x kept increasing as it was going through the loop. My function, that x always stays at 16. The static x keeps incrementing by 1. So every time we stepped into this static x, we went ahead and incremented it. Right? It retained its value between function calls. All right. So about the only reason then you would declare a static variable is if you need, for some reason, the variable to retain its value between function calls. Right? So one thing I can think of, if for some reason you wanted to count how many times that function was called, you could put a counter in there that would keep track of how many times you went into that function. We don't use static variables too often. So don't be surprised if you're not using them in your homework, but this is a topic that you should be aware of. At some point, if you need a variable and it needs to retain its value when you start working with multiple files, then you may need to return to this more advanced concept. All right. And the end of the lecture then just has a slide then comparing these different storage classes, telling you when these variables are accessible, right, where they're stored, right? Everything's stored in main menu except for this register class or main memory. If I said main menu, didn't mean that, right? Auto storage, so everything we've been working with up to date has garbage if it's not initialized. Static then is initialized to 0, so that's the only thing that's different so far. And so any global variables that we create are part of the static storage class. If we don't initialize those will be initialized to 0. Right? That should give you sort of a better idea of what we mean by scope of a variable, right? What happens when you use variables with the same name, how they're hidden when they're accessible, right? And you'll get much more experience as you write more and more functions and more C programs.